Hello folks and welcome back to ECMath. Today we're going to move right into section 3.2 with an introduction to logarithms. Today we are not going to talk about log graphs, but we are going to talk about what is a logarithm, how do you evaluate them, and what are the important properties. So the idea of logarithms arose in the process of solving equations, and eventually you could imagine this might have started as a more complicated equation, but there's a category of equations that you get them down, you solve them until you get to a point where you have an unknown exponent with a known base equal to a number. And you need, or some way, to solve for that exponent to figure out what it would be, other than just guess and check. So here you could probably guess and check, plug in numbers until you figure out that it is 6. But that's the tool that logarithms are built for. So let's go to an exponential statement that doesn't have any unknowns, that has all the variables filled in, and I'm going to show you how to rewrite it in logarithm form. And then we'll take apart what it means in a little bit. So here we have 2 to the 5th is equal to 32. In log form, we are solving for the exponent. And what we're going to write is the log base 2 of 32 equals 5. So we say log base 2 of 32 is 5. Is how we talk about it. And let's look at where the pieces went. So just a color code, sorry about that. The exponent moves to the other side of the equal sign. The base of the exponent becomes the base of the log, and the result over here, which we're going to call the power, moves here to the argument of the log, the thing sort of inside the parentheses of the log statement. And you can sort of imagine that if you see the base fixed as the base in both cases, then you're really just changing the roles of the 5 and the 32. Let's look at this another way. Instead of using numbers, we're going to use shapes. You can imagine these shapes represent variables, but I think it can help to see the structure if you're thinking about shapes instead. So we could say the log base b of square is equal to triangle. And when you see a log statement like this, this is another way to think about it, is saying, okay, b to what power will give me the thing that is next to the b, the thing that is in the argument of the log. B to what power will give me square? Well, if we rewrite that in exponent form, we can see that b to the triangle power equals square. So the answer is b to the triangle power should give you the square. Maybe that's a little goofy. So you can also think about this as, without the triangles, you could say, okay, the log base b of x, if the log base b of x is equal to y, then b to the y is equal to x. So there's this translation or switch between the x and y variables in this context. And of course, I drew that arrow going to the left, but you can also translate the other way, like we did in the first problem. So you can write exponential problems as logarithms, and you can write logarithm problems as exponents. It helps me to understand logarithms to sort of name the pieces of logarithms, or logarithm statements and exponential statements. So I'm going to label these pieces with the hope that it helps you sort of understand or remember what everything comes from or where it should go. So b, whether we're looking at shapes or variables, is called the base. And it is called the base, on both sides here, whether you're looking at an exponential statement or a logarithm statement. Now, on the left side over here, the thing that's sort of inside the log, like after the base, I would call that the argument to the log, and you can think about that as being the input to the log as a function. We're taking the log of something. Well, that thing that's inside there is the argument of the log. And then we can call the whole thing the logarithm. So when we say, the logarithm, it's not just the words log, it's the logarithm with a base and an argument. And the logarithm refers to the log base b statement, but it also refers to, the square or the triangle, what we've called it. Now, so we have a base, we have an argument, and we have a logarithm. Base, argument, and logarithm. On the exponential side, we still have a base. Here, we might call something the argument again because it's sort of an input, but we're going to call this the exponent because that's what it is. So that's the exponent. And this is kind of goofy, but we have a word for the whole thing that we probably don't use very often, but this could be called the power. Like the, 2 to the 5th is the 5th power of 2. So that's what we mean when we refer to the whole thing, and that, of course, could refer to this. So we have the base, the exponent, and then the whole thing is called the power. On the left side, we have the base, the argument, and the whole thing is called the logarithm. But let's look at the connection between them. The connection is this triangle. On the left side, we call the triangle the logarithm. On the right side, I'm going to zoom out and spoil the punchline here. On the right side, we call the triangle the exponent. And that means a logarithm is an exponent. A logarithm is an exponent. So whenever I write, log base 2 of 64, I'm thinking about an exponent. This whole thing is some exponent of 2. And specifically, if I was going to evaluate that, it would be 2 to the what is 64? Well, 2 to the 4th. Nope. Sorry, 6th is 64. So this whole thing refers to, or evaluates to, the number 6. When you switch that form, you're really solving for the exponent. If you have an exponential thing, you switch it into log form, you're solving for the exponent. But this key idea that a logarithm is an exponent is actually very helpful when we start thinking about log rules, because the rules of logarithms that we're going to see in the next section actually match with the rules of exponents that you already know. So, key idea there about logarithm. So, let's do some examples. The first thing one of the things you might get asked to do in a logarithm problem is evaluate something. And often people get confused because there's no equal sign here. They say, what is this equal to? What am I supposed to do? Well, when you see the word evaluate, that is basically a command to you, the reader or listener, to find the number that this is equal to. You're pretending that you're a calculator, right? I have a calculator that I could type in log base 3 of 81. I'm not going to do it because that would spoil the surprise. But this is basically a calculator command. So how do you approach it? Well, remember that a log is an exponent. So we can turn it into an equation. It kind of helps me, at least to start out. Say, okay, if log base 3 of 81 is equal to something, and I'm trying to find that something, then we need to translate this into exponent form. So this is going to be saying the same as 3 to what power equals 81. And then you're going to go through your mental list of powers, and if this is a power that you know, then you can figure out what the number is. So if 3 to the 4th, which is true, is equal to 81, and you can check that if you need to, then we say that the log base 3 of 81 is equal to 4. So you erase the question mark and you write 4. There's no x's, right? The final answer here is the number 4. That's the answer if you're asked to evaluate a logarithm. Sometimes folks give equations or things which is not quite the answer to the question that this is asking. Evaluate says, what number is this? All right, but this is the general strategy. Write it in exponent form, use what you already know about exponent properties, and to solve these. Here are 4 more. Go ahead, and if you're feeling experienced, pause the video and try this now. All right, so let's run through these. Log base 3 of 1/3 is asking the question, 3 to what power is equal to 1/3? Well, how do you get a fraction with the same base? You use a negative exponent. So 3 to the negative 1 is equal to 1/3. So log base 3 of 1/3 evaluates to -1. Log base 5 of 25. Here we're changing the base. So you always pay attention to the base. This is saying 5 to what power equals 25? That's a question mark. Well, 5 squared equals 25. So we say that this log evaluates to 2. Log base 5 of 1. This is asking you 5 to what power equals 1. There's only one power that this can be. 5 to the 0 is equal to 1. So we say log base 5 of 1 is equal to 0. And then for the last one, log base 7 of 50. This is saying 7 to what power equals 50. Now, this one might be a little bit of a trick question. Sorry, I sprung that on you. Sometimes with logs, you have to approximate. So the exact answer actually is just this is its own exact answer. Log base 7 of 50. But you could approximate it by recognizing that 7 to the 2 is 49. So the exponent here needs to be just a little bit bigger than 2. So you could say log base 7 of 50 is approximately, I guess you could say is approximately 2 or maybe approximately 2.1. And while we're here, why don't I show you how you can get these on your calculator. So again, you have to have the newest operating system to do logs with easy bases. Otherwise, you have to use something called the change of base formula. But you can do alpha F2. Alpha F2. You can go to option 5 that says log base. You can do log base 7 of 50. Let's see how close we were with the estimate of 2.1. Actually, we were off by 1/10 because 49 is so close to 50. Log base 7 of 50 is actually 2.01. So why don't I add a little 0 in there. But notice that this log base 7 of 50 goes on forever. And that's a key idea. When you have a log, I'm going to make some space here. When you have a log that doesn't evaluate perfectly, then this is an irrational number. Non-terminating, non-repeating, kind of like pi or e, but instead of being, actually less like pi and e, but sort of like, how square root of 2 is non-terminating and non-repeating. This is another example of something where it's not a perfect logarithm. It doesn't evaluate out nicely. So it's just an irrational number. So if you have a problem and it asks you for the exact answer and the answer would be log base 7 of 50, as weird as that is, you should just leave it there instead of trying to approximate it. While we're still in this section with evaluate, and I think I mentioned this earlier, but one thing students sometimes do is they turn something, they say they're doing log base 3 of 1/3, and they turn it into exponential form, and they write 3 to the -1 equals 1/3, then they'll box this as their final answer. That is not the final answer. That shows, yes, you're thinking about logs correctly, you solved for the logarithm, but the logarithm is actually just the exponent. Remember what we said, a logarithm is an exponent. So in all of these problems, if it's asking you to evaluate, the answer you give should be the single number that is the exponent, or maybe in this case it's the exact one, the single number or phrase that is the exponent, not some other random exponential phrase. Be really careful about that because you will lose points on assessments when that comes in. All right, here's another type of problem, and they're going to seem super similar to the last ones, but here's the key difference. In all of these problems, we're given an equation already. We don't have to write an equation, and this one is not necessarily asking us to solve or evaluate for anything. It's just saying switch the form. This is a really useful technique for solving equations later down the line and just in general. Sometimes when you have a log, it's better to express it as an exponent. Sometimes when you have an exponent, it's better to express it as a log. So you need to be really, really swift at switching between these forms. So let's take a look. 2 to the y is equal to 13. Put this in log form. How do you do it? This is the base. Log solves for the exponent. And so then this thing that we've called the power is going to be the argument. So we're going to say that this translates to log form as log base 2 of 13 equals y. So in this case, log base 2 of 13, again, 2 is not like a nice power of 13. Or 13 is not a nice power of 2, I should say. So this would be the final answer solved for y. Log base 2 of 13 is some irrational number. Don't know what it is exactly. That'd be a good final answer. All right, next example. Z to the 1/2 equals 100. Actually, I'll make you the same offer as before. If you're feeling accomplished, pause the video now and try these 4, and then just skip to the end. And if you had a chance to try that out, let's take a look. So Z to the 1/2 equals 100. And by the way, I've written this as a 1/2, but you might also see this as, oh, square root of Z equals 100, right? Because what is a 1/2 but the same as a square root, a 1/2 power, I should say. So you might see stuff in root form that's sort of a similar question. Okay. What's the base? What's the exponent? And this is the argument, or going to be the argument of the log. So we will write that the log, right up here, the log base Z, so Z, it doesn't matter that that's a letter, it can still be the base of a log. Log base Z of 100 is equal to 1/2. Now in this case, we kind of actually went backwards from solving it, but this isn't asking us to solve. This is just saying switch the form. We have now switched the form, so this problem is completed. All right, let's practice switching the other way. So what if we have log base P of 625 equals 4? I wonder if we could solve for P. Well, there you can't just like divide by log, right? So actually, here's something that people will often try. Some kind of nonsense like this to solve for P. Guess what? Doesn't work. This is totally illogical. A logarithm is nothing without a base and an argument. So dividing by the letters log does absolutely nothing. It's completely meaningless. So something to watch out for. Instead, what do? You translate it into exponent form. So this is the base. This is the argument. We'll just do arg. And then this is the logarithm, but we know that the logarithm is the exponent. So 4 is going to be the exponent, and this will translate into P to the 4 equals 625. Now, I wonder if we could solve for P. 625 is 5 times 5 times 5 times 5, right? Or 25 times 25. So wouldn't that mean that 5 to the 4 equals 625? So in this case, I think we could solve for P and get P equals 4. But if it was just asking us to switch the forms, this would be the final switched form answer. All right, and let's look at this last one. Log base 2 of 2 to the m equals 18. So this is a situation where you have like an exponential statement inside of a logarithm statement, and often these are both like the most confusing, but also the simplest at the same time. So let's write it out. This is the base. This is the argument, which is going to go on its own side of the equation, and this is the exponent. So if we translate this, it's going to be 2 to the 18th equals 2 to the m. The entire argument here goes on the left side of the equation over there. Now, can you figure out what m might be? Yeah. Since 2 to the 18th is equal to 2 to the 18th, m had darn well better equal 18. So this is kind of using a parallel structure. And this is using one of these properties of logs called the inverse property that we'll come back to in a little bit. But almost every property of logs can be figured out or derived by thinking about its equivalent exponential form. We'll come back to those properties of logs in a little bit. I wanted to give you 3 important ground rules for any kind of logarithm statement. So for this section, we're going to assume that we're looking at a statement of the form y equals log base b of x. So x is the argument and y is representing like the logarithm. The first rule is that the base must always be greater than 0. You're not going to have a log that makes sense with a negative base. And the reason is that if you translate this to b to the y equals x, thinking about an exponential function, well, we have the same rule for exponential functions, base greater than 0. If we have a negative base in an exponential function, we end up alternating between positive and negative and have weird things going on, and it's the same for a log. So no bases less than 0. If you see that, it's your non-logical statement. It's not going to happen. It's not going to work. Also, your base needs to not equal 1 for this to be a useful logarithm statement. So if I have y equals log base 1 of x, that's translating into 1 to the y equals x. Well, there's only one number that's going to work for, and that's only true if x equals 1, and otherwise this is, again, a completely irrational statement. So when we had exponential functions, again, we said it's not an exponential function if the base is 1. So same reason, we can't have a base of 1 here because it makes this sort of goofy, trivial thing, and it doesn't behave like other good logarithms. And then finally, and this is the most important rule of logs because it lets us sort of think about the graph of logs, which we'll come back to again later, the x, the argument, must be greater than 0. Must be. There is no such thing as taking the log of a negative. It is an irrational statement. So here's why. So let's say I had log base 2 of -4. And I wanted to evaluate that. Well, that would translate to 2 to the what equals -4. But guess what? 2 is positive, and there's no way that you're going to take any power of 2 and get a negative number, right? 2 to the 6th? Oh, nope. 2 squared, that's 4. But how could you get a negative? Well, could you try 2 to the -2, right? Like that you might try. No, that gives you a quarter. There's no way that 2 to the will ever equal -4. And if you think about it in the language of exponential functions, 2 to the x looks like this. Will that ever equal -4? Never. Those two lines and graphs will never meet. So it's totally illogical to have a negative input to a log. It can never, when you translate it to exponential equation, it can never make sense. It can never have a solution. So we say that the domain of the logarithm function is x greater than 0. Here, let's write that out and actually do a couple examples. So, idea. The domain of y equals log base b of x, and the base can be anything, is x strictly greater than 0. Not greater than or equal to, but strictly greater than 0. And roughly the reason that it's strictly greater than is, think about that exponential function again. Does it ever equal 0? No. Then there's no way a logarithm, if you translate it in an exponential form, could equal 0 either. So that's why we have the domain strictly greater than 0. So now let's say we had a transformed log function, so maybe some kind of equation or something, and we get y equals log base 3 of x minus 1. We're asked to find the domain. What do? Well, you isolate that argument, right? So here it's x, but this is x minus 1. You isolate that argument and set, that argument greater than 0. So x minus 1 is the argument. Set that greater than 0 and solve. In this case, add 1 to both sides. And we get x greater than 1 is the domain. What about log base 1/3 of 8 minus 2x? So first thing, don't be thrown off by that base of 1/3. Doesn't matter what the base is, right? This statement about the domain was true for any log of any base. So it doesn't matter that it's 1/3. You're going to do the same thing. Take the argument. Set that greater than, not equal to, but just greater than 0, and solve. So to solve this one, let's add 2x to both sides. So we get 8 is greater than 2x. So dividing by 2. 4 is greater than x. Or x is less than 4. And this is kind of a weird one. If you think about a transformation, this negative on the x is actually reflecting the graph of log, which I know we don't know technically yet. But if you were to shade the solution set to this one, it would actually be this way. Even though most logarithms have a shaded solution set going to the right. So that's something to watch out for, but you can always find a domain of a log just by setting up an inequality and solving it. Okay, two other things you might see. As you're working through problems, you're looking at your book, you might see a log without a base, right? So you might see log of 100. Whenever you see the word log without a base, this is called the common log. And the common log always has an implied or implicit base of 10. Why? Well, because we live in a base 10 world. Our number system is a base 10 number system. So when we've been using logarithms, when logarithms were first developed, it was just assumed that they had a base of 10, and that's where they came from. And then only later on were other bases like developed. So the common log is the log with base of 10. So if I wrote log base 10 of 100, or log of 100, I'm saying log base 10 of 100, and this is again saying 10 to the what equals 100. So we would say log base 10 of 100 is 2. And just to test that, why don't you try to find the log of 10,000? And just to check that in, this is saying, this is a base of 10, so this is saying 10 to the what equals 10,000. Well, you can kind of count the zeros. There are, since 10 squared is 100, 10 to the third is 1,000, 10 to the fourth is 10,000. So log base 10 of 10,000 should be 4. And there are 4 zeros there. Okay, the other common log you'll see is the natural log. This is the log with a base of e. And remember, e is not a variable. E is the irrational number that is approximately equal to 2.7182, etc. But non-terminating, non-repeating, button on your calculator, all that goodness. We talked last time about how e to the x has some special properties about rate of change. So it turns out that when you're doing problems and you get to choose a base, any base in the world, e is probably the best base to choose. So same deal, if you're doing log problems and you get to choose a base, e might be the best base to choose. So natural log is just log base e. So if I write, for example, natural log of e to the 6th, I have to do an exponent here to make this work out tidily. This is saying, well, that's equal to what? So I'm saying base e to the what is equal to e to the 6th. So natural log of e to the 6th would be 6. Whenever you see that natural log, we don't write natural log base e, by the way, right? Don't actually write that on your paper or in your, I would say you can write it on your paper. Don't write it in your final answer. Just write natural log in your final answer. Another thing to not write in final answers, actually just write this here. So don't write ln e, base e of anything. You can show it in your work, but don't give it in final answers. And another thing you should not write in final answers is log base e. Again, you can show it in your work. That's fine if it helps you think about it. Not okay in final answers. We need to use the ln phrasing correctly, basically. So natural log of 4. Let's test that out, put that to the test. So this is saying e to the equals 4. Now, 4 is not a nice tidy power of e, so it might be hard to find this, but we can explore a little bit because we know e is like basically 2.7. So I'm really asking 2.7 to the what equals 4? Well, let's check 2 to the what equals 4 would be 2, but 3 to the what equals 4, well, that would have to be something only a little bit more than 1, 1 point something, something, something. So I bet that e to the what equals 4 is, maybe 1.5-ish. And let's actually check that. And I want to show you how to check that on a calculator. Calculators always have a natural log button. That is the button, we said 2 logs most important. Well, you have your common log button right here, which is also the same button as the 10 to the x button, no surprise. And you have your natural log button right here, which is right by the e to the x button, because those are, of course, related. So natural log of 4, you don't have to close those parentheses, but it can be nice, is about 1.38. So I said it was 1.5, kind of close, but that's just an approximation. Okay, we are closing in on the end of the video here. There are 4 properties of logs that you need to know. And I'm serious. A lot of folks think they can get away without knowing these properties by heart. The deal with logs, though, is we're going to be solving some really hairy problems, some really complicated equations with a lot of steps. Logs are just part of it. Every time you get a chance to use these properties, you should. So you should make the effort now to really get these properties down while they're easy so that they can help you in harder problems instead of being a hindrance later on. So the first property, we'll make these a little larger. The first group are kind of about 1 and 0. And we've seen some examples like this before, but the basic property is that the log base b of b, whatever that base is always equal to 1. Well, why would that be true? Well, if you put it in exponent form, this is saying b to the what equals b. Well, it's only true that b to the 1 equals b. So that's why this property is true. Let's check this out. ln of e, this shows up all the time. And a lot of times folks will get that on the final answer. They'll box it and they'll lose points. And they say, why did I lose points here? Well, because natural log of e is the same as log base e of e. We know by this log property that has to equal 1 because this is saying e to the what equals e. So whenever you see something like ln of e, it's 1, always. Next property, log base b of 1 is equal to 0. Why would that be true? Well, we had an example like this earlier. B is the base. B to the what will equal 1. Well, there's only one thing that will work. Since our base can't be 1, right? Base is not equal to 1. So any other base, well, the only number that that's true for is 0. So that's why anything where you're taking the log of 1, you get 0. That's actually what I wrote here. Log of 1, doesn't matter what the base is, but remember that log is log base 10, so log base 10 of 1 always equal to 0 because 10 to the 0 is equal to 1. Cool property. Okay, the next properties are paired. I'm going to zoom in on those a little bit. And these are paired, and they're called the inverse properties. And we have this idea that logarithm functions and exponential functions are inverse relationships of each other. We'll talk more about that when we talk about the logarithm graph. But when you have a log and an exponent nested, right? So here they're nested. We have a log on the outside and an exponent on the inside, or we have an exponent, or we have an exponential function on the outside, kind of here, and a logarithm function on the inside. Those are also nested. Those are going to reduce out with each other. And this is one where it's really nice to simplify equations. If you start, really can be confusing in the middle of a problem. So let's take a look at it again. Log base b of b to the x is equal to x. Why would that be true? Well, let's evaluate this side. This is saying b to the what equals b to the x. Right? This is the logarithm part saying this. The argument is saying b to the x. Well, b to the x is equal to b to the x. So that's why this has to equal x. Log base b of b to the x is always equal to x. They're inverse functions. They will reduce out if you have the same base. How is that useful? Well, say you have a natural log of e to the 10th. Natural logs are really hard to evaluate. How do you do it? And e to the 10th, I don't know what that is. Well, remember that this is log base e of e to the 10. And by the property, we can just say that this is equal to 10. That's all you need to say. But if you did want to show the work, this is saying e to the equals e to the 10. Well, it has to be 10. Second property is a switcheroo of that property. So we have b to the log base b of y will always equal y. And those could be x's too, right? It doesn't matter what the x or y or the letter actually is in there. But we have a matching base, and we have a logarithm statement in an exponent. So here we have an exponential statement. We have to turn it into a logarithm statement, right? These were all logs, and here we have to turn it into a log. So we're going to have log that I'm turning this into base b, that's the b from the base, of y, that's this y over here, because I had an exponential statement, I'm turning it into the log, is equal to whatever the exponent was. Well, the exponent was also log base b of y. So we have base to the power equals the exponent, or base to the power equals the, base to the logarithm equals the power. Here we have log base b of that power equals the original exponent. And so by sort of parallel structure, it better be true that y is equal to y. Okay, and how can we put this into practice? Well, what if we're doing 2 to the log base 2 of pi? And we're trying to evaluate this, right? They're all numbers. We should be able to evaluate this. This can get really hairy and messy. If you use this property, you can just say, by the property, it's equal to pi. And if you had to translate it, you'd be saying, okay, well, let me put this in log form. This is log base 2, because this is the base of what is equal to log base 2 of pi. Oh, and then it has to be pi. But you don't want to have to write that out every time. That's a huge pain. It's easier to just say, using the inverse property, that's equal to pi, or whatever it is. And note, by the way, I chose pi there to show you, you can't have irrational x's too, right? You don't always get logs that evaluate nicely. But even if you have a scary pi in there, all your log properties will still work out. And I borrowed this slide from your book to remind you that all the properties I just said, they also apply to common logs base 10 and natural logs base e, as well as general logs with any base, right? They're the same property, just written in different ways. But it can be confusing. You know, a lot of people will do this property all the time, but as soon as they see log of 10, they will not write that it's 1 because they're not used to seeing that. Make sure that you're applying all these simplifying properties no matter what the base is, even if it's e or if it's 10. All right, to close out our video, I think this is a nice way to close, just with another set of problems. We'll talk about estimating logs. We kind of did a little bit of this before. This is a really nice trick that you can do with log numbers. Log of 487. How do you do this, right? I don't have my calculator with me. Like, what if I needed to know this logarithm? Well, remember, you can kind of use the idea of a sandwich. So this is saying log base 10, remember this is a base of 10, of 487, is really saying 10 to the what is equal to 487. Well, the nice thing about 10, and this is why this is really nice to do with powers of 10, is you know the powers of 10. We know that 10 squared is equal to 100, and we know that 10 to the third is equal to 1,000. So, what is this exponent? Well, it better be between 2 and 3. So we could write maybe that 2 is less than log of 487 is less than 3. That's definitely we know, and we could even estimate it. We could say it's approximately 2.5 question mark, you know, and then you could get a little more precise if you wanted to. But that's how you estimate logs. You try these next two. Here, let's check that in. So this would be saying 10, well, let's do a sandwich here. This would be saying 10 to the what is equal to 58,736. Well, we know that 10 to the fourth would be 10,000, but 10 to the fifth would be 100,000. So this number is somewhere in between there. So we say that this is somewhere between 4 and 5. You know, it's between 4 and 5. You could say maybe it's approximately 4.5, 4.4. You know, you can get more precise with a little more careful estimation. But that's a really nice way to approximate logs. And that's one of the key uses of logs is like, if you know just how many digits you have, you actually already know the log base 10 of that number. That's one of like logs tell you the size of a number. And that's why when you look at scales like the magnitude, the decibel scale for audio or the Richter scale for earthquakes, those are actually logarithmic scales where a number that is above it on the scale is 10 times more than the number below it. It's telling you kind of the magnitude or size of the number without having to write all those dang darn zeros all the time. All right, and then the last practice, log base 5 100s. This is saying 5 to the what equals 100. Well, you try. Sandwich it. 5 squared is 25. 5 to the third is 125. So this is kind of like the other one. It's better be between 2 and 3. Maybe a little closer to 3 this time. So you could say, oh, maybe that's 2.8. I don't know. And you can, of course, check that with a calculator to be sure. But that's just a good way to check and estimate all of your logarithms. So to recap today, we have looked at the definition of logarithm. We did a bunch of examples about how you evaluate them. We did some examples of rearranging the form. We looked at some key properties, and we learned how to estimate logarithms. That should be enough to get you through some initial problems. Next time, we'll talk about how to graph logarithms and how those kind of come together. So let me know what questions you have, and I'll see you all next time.